Earlier in the semester, we did the section on introduction to calculus. And this is where we talked about, okay, you have some kind of curve like this, and you want to approximate the area under the curve. And you could break it up into rectangles. That rectangle, and maybe this rectangle, and maybe this rectangle. And so you can approximate area, and you have gaps, or you might be low, or you might be high, and that's what we're going to talk about in this section, is build on that. So use sum of rectangular areas to approximate the area under the curve. When I was in my teaching credentialing program, we all had to do a presentation. I think it was math specific, but maybe it wasn't. But there's a guy in that program that was, he was a math guy like me. And he had a really interesting way of demonstrating calculus. And I wish I had all the props he had, but he had like a bowl. You want to find the volume of the bowl, and you can put a couple of big balls in there and estimate, you know, the volume of each ball. And he said, okay, well, you can get a little more accurate by pouring marbles in there and kind of how many marbles you had, you know, the volume of each marble, but you still have gaps. You can get like BBs and put BBs in there, know the volume of each BB, but you still have gaps. And they talk about getting smaller and smaller objects to fill the bowl so you can get the volume of that. And then he got to sand at one point, putting sand in. He would first start with lava rocks. Who's ever seen lava rocks? And they're not consistent size, right? They're just, you know, how many with that? So that didn't work. So he went to something uniform. And that's kind of the idea here is we're going to be talking about breaking that area under into a bunch of little rectangles. We want to get eventually the smallest one possible. Now, are we really going to add up an infinite number of these? No. We're going to go to these formulas that let us like the summation of n times n plus 1 over 2 or something of that nature to help us come up with what the actual area is. That is the long way to do it. We will be doing it in a very short way, much like we did at the end of this last module, where we did the integral of that thing equals this, because we'll see that, and this justifies it. The difference is for there, that was an indefinite integral, so no endpoints to it. Now we're talking about having specific endpoints of this interval. So like in this problem here, we have an A and we have a B. We have a specific amount of space to work with, and we can now measure that. And that's where it gets to be a little more complicated, but it really doesn't have to be. So that's the idea about what's going on. We're going to break this up into different rectangles. So part of it is we look for this B minus A over N, and that's what we call our delta X. B minus A over N, I guess it's right down here too. And that tells us how wide these intervals are. So if it was like B equals 4, A equals 1, and N equals 5, it'd be 4 minus 1 over 5, which is 3/5. Or, yeah, 3/5. So each interval would be 3/5 wide. So that's what I was saying, this right here. And then each interval itself would be determined by xi is the initial one, your A is x sub 0, plus whatever your I is, if I is 1 or 2 or 3 times the delta x, tells you how far it pushes it over. So you might start with, you know, an x0, x1, x2, x3, and finally you get to maybe an x5 if there were 5 intervals there. And you have a left and a right side of the interval. Just a lot of little pieces like that to consider. So here's our actual definition. And we talk about the term partition and a regular partition. So a set of points P equals xi, for I being 0 through n. A is going to be equal to the left endpoint, and B is the right endpoint. And just the way we go from left to right, x0, x1, x2, let me do from your perspective, x0, x1, x2, x3, across until we get to B. And we form these intervals, x0 to x1, x1 to x2, all the way to the end. And those are called the partitions, broken up into intervals. If they're all the same width, which for the purpose in the beginning of this, they will all be the same width, then those are called regular partitions. They're all the same width. We're all 1/2 or 0.2 or something like that. They're all the same width. Oops, did not do that. I apologize. I don't even know what I did. Okay. Now we have two concepts, and again, this I feel like we touched on this in the start of the semester. Was that we had left endpoint approximations and right endpoint approximations. So when you're talking about an interval, this interval, here's the left end, here's the right end. And it could be that left end is below the curve and right end's above the curve, or vice versa. Again, I should probably do from your perspective. Left is below, and right is above, or vice versa. And so one might be an underestimate, one's an overestimate. So left end approximation is xi minus 1 to xi. Construct a rectangle with the width delta x and the height equal to xi minus 1. So it's on the left end of it. And then the area is that f evaluated at xi minus 1 times, so that's your height times the width. And this is your approximation. A is approximated by the sum of these, and L means left of n, the number of intervals you have. So this is a calculation for the left end. And if you notice the indexing, I equals 1 to n. So it's going to be x sub I minus 1, 1 minus 1 is 0. So it starts off at x sub 0, then x1, up to xn minus 1. Contrast that with, and this is a visual of what that looks like. So it's on the left end in each case here. These all happen to be, because based on how the curve is, they're all below the curve. The curve could be concave down, and it might be above the curve then. So that gives you a visual. I know you have people taking notes on this, so I don't want to rush too much. But then we also can do it from the right side. And then on the right side, that would make it concave. Well, I shouldn't say that could be above or below the curve again. So the right end approximation looks very similar, but we use the R for right. And in this case, instead of starting at x sub 0, we start at x sub 1, and it goes up to x sub n. So I equals 1 to n. It starts at x1. So it's on the right side of each interval. It's not like one's better than the other. One is going to typically be under, the other above, and the answer is usually between them. And some people will find the left and then find the right and then average the two, and that gets close to it. And again, that's not the long-term thing you're going to be dealing with in calculus, where we're developing the concept of area under the curve now, and we'll be getting the exact value very, very soon. So if this was a business calculus class, we probably wouldn't be covering this part. Okay, here's a visual of the right end of the same curve. So notice here, they're above in each case. It's a little above the curve, or the other one was below. It doesn't mean that the actual value is right between them as the average of the two, but it's closer. This is the example of the right end approximation. Okay, so let's do an example with this. Here's just showing the calculation. Here's the left, here's the right. The left gave us 3.4375, and then the right calculation, they do it down here, was 5.6875. So that's quite a big difference there. Now that's over 2 difference, given the size of the other values. That's significant. So let's do our own approximation. We're going to find left endpoint and right endpoint approximations to the area under the curve of f of x equals x squared on the interval from 0 to 2. So I'm going to draw a picture of this, and I think a picture helps to visualize it quite a bit. I mean, you don't have to draw a picture. Come on, there. So if we were to look at this, I'm going to change colors for the color of the curve. Might look something like this. And our intervals would be, that says 0 to 2, so 2 minus 0 over 4 is going to be 2 over 4, which is 1/2. So we'll have a point at 0, then 1/2, then 1, then 3/2, and then 4. So our left-hand approximation means we'd start at 0. So we do f of 0 times the 1/2. This is L4. Plus f of 1/2 times the 1/2. Plus f of 1 times the 1/2. Plus f of 3/2 times 1/2. And let's get some numbers behind this. That's 0 plus 0.125 plus 0.1 or 0.5, excuse me, plus 1.125. And if I draw a picture of these, let me change colors again. I'll go to green. There's the first one's down there, it's 0. Then it comes up and it's over. And it comes up and it's over. It's up and it's over like that. So clearly an underestimate, and we end up with 1.75 is the area estimate, 1.75. So that's left. Let me draw a picture for the right. Again, have this curve. And I'm going to break my interval up again the same way. So we have 0, then we have a 1/2, then we have a 1, then we have a 3/2, and then we have a 2. And if I go draw my rectangles, this time on the right end, it's going to be doing this type of thing. And then we're going to be doing this, and here, and then here. So that's clearly going to be over. Our calculation would be R4 equals, instead of starting at 0, we're going to start at 1/2. So f of 1/2 times 1/2 plus f of 1 times 1/2 plus f of 3/2 times 1/2 plus f of 2 times 1/2. So the first 3 we already saw in the last one. In fact, those first 3 are the answer for L4 because the first term in the L4 was 0. So what that looks like is going to be 0.125 plus 0.5 plus 1.125 plus, and I just have 2 for the total, the last one. So this adds up to be 3.75. So given the magnitude of these numbers, 1.75 to 3.75, a difference of 2, that's a big difference, given that we're looking at 1.75 and 3.75. So the error here is pretty big that we're going to encounter. If we were to take more intervals, if we did 20, it'd be a lot better. If we did 50, it'd be a lot better. If we did 1,000, it'd be a lot better. It'd be pretty darn close then. Probably close enough for our purposes. But we're going to do, as we go on, we're going to do an infinite number of them. So Don't worry, it'll get really cool. Questions there before we go on to another example? No? So the next one we're going to do is f of x equals 1 over x on the interval from 1 to 2 with n equals 4 again. So we're going to start writing that down. And we're going to do both the left and right endpoint approximations. Okay. So in this one, sketch left endpoint and right endpoint approximations for f of x equals 1 over x from 1 to 2 and equals 4. So our delta x is going to be 2 minus 1 over 4, or 1/4. If we were to graph this, I'll do two graphs, one for the left end, one for the right end. So it's 1 over x looks just something roughly like this, especially for the area that we're looking at. And we'll do another one for and it's going from 1 to 2. So we'll say here's 1, do 1.25, 1.5, 1.75, and 2. These aren't, the intervals aren't drawn all that well. And for the left-hand approximation, we're going to go up to the curve, come over and down. So now this one looks like it's going to be above. It's going to come over and down, over and down, come over and down. Whereas the right-hand approximation, we come up from the right side, hit it, and go over to the left and go down. Left. So which one's going to be bigger, do you think? Yeah, left hand. So we have L4 in this case is going to be f of 1 times 1 over 4 plus f of 1.25 times 1 over 4 plus f of 1.5 times 1 over 4 plus f of 1.75 times 1 over 4. So that comes out to be, I'll give it to you, 0.7595 for the left-hand approximation. Whereas the R4 would be, starts at the right-hand side of the interval, so f of 1.25 times 1/4 plus f of 1.5 times 1/4 plus f of 1.75 times 1/4 plus f of 2 times 1/4. And this one comes out to be 6.6345. If we wanted to be more accurate and closer together, it would increase the number of intervals. So these aren't too far apart, but you know, someplace in between is probably closer to like, I know what it is, it's 0.69. Actually goes on forever, but. Okay, got one more I want to see if we can do anything on this. And then there's one more part of this section, one more subpart called Riemann sums that we'll get to next time. Okay, the last problem here is, see, they're showing as you get more intervals, it gets more closer, and you end up with less error. See, these are all over, but not as much over. Okay, so we're going to do one more here, and it says approximate the area between the x-axis and the graph f of x equals x squared plus 4 over the interval from 0 to 2. So what would our delta x be in this case? It's going from 0 to 2. So what would that be? There are 4 intervals. What's that? 2 minus 0 over 4, which is 1/2, or 0.5 is fine. So they want us to do, looks like left-hand approximations. So L4 is going to be f of 0 times 0.5 plus f of 0.5 times 0.5 plus f of 1 times 0.5 plus f of 1.5 times 0.5. So it looks like it's going to be 4 times 0.5 plus, it's a formula 0.5 squared, so it's 4.25 times 0.5 plus 5 times 0.5 plus 6.25 times 0.5, and you come up with 9.75.